Microsoft research in India, and he'll be talking about concentration inequality.
Yeah, so I should, what's that? I should warn you, I don't mix.
Wait a minute.
Oh.
Okay, we're going to start. Okay.
Yeah, I should warn you, I don't mix rapidly anymore. I used to, but this talk is still something to do with probability, but not with Markov chains so much. It has to do with the traditional Azuma or martingale inequality. I'll remind you of it. It has to do with an improvement of that. So x1 through xn is actually a martingale difference sequence, right? If the expected value of xi is 0 given the, so for every fixed value of x1 through xi minus 1, the expected value of xi is 0. That's a martingale difference sequence. And the thing that I want to focus on is in the traditional Azuma and martingale inequality, you assume another condition, which is an absolute bound. On the martingale differences. And this is what we would like to attack, because it'll turn out, and I'll show you some examples, there are many examples, where this is too high a bound that you have to put, because it's got to be absolute. Okay. But anyway, the conclusion of the usual inequality says that the probability of the sum of xi greater than or equal to t is less than or equal to c e to the minus t squared another c over n. The best way to remember this, and the way I want to remember it, not just this quantitative form, but in the following form, it says that the sum of xi 1 through n is concentrated. That means with high probability it lies in an interval of length order root n. So this is the form we remember it, right? If the absolute differences are at most 1, these are martingale differences, the absolute xi is at most 1 each, there are n of them, the concentration is in an interval of length root n. Okay? So as I said, what I would like to attack is this condition. I would like instead only to impose a condition that typically it's bounded by something, and in terms of the typical bound, I would like to get this result instead of an absolute bound. So what I would ideally like, intuitively, is suppose this is true, with high probability this is true, then I would like to conclude this. I'll make a precise statement when I get to it, but that's the intention of the talk, right? That's the main point of the talk. I'll give you 3 examples, 3 sort of salient examples which have been worked on for quite a bit. The first is bin packing. Maybe I'll give you only 2, but here you have stochastic bin packing. You have IID items, n items, they're independent, and let's say the expected value is mu. This is only interesting when mu is much smaller than 1, and the variance of each thing is sigma. So these items are coming along, and you would like to pack them in the minimum number of bins of capacity 1. Minimum capacity 1 bins to pack all these fractions. This is a regular bin packing problem, right? This is the optimal number of bins. There's been a lot of study of whether such a thing, many other things like that, but this particular thing, is it concentrated in an interval about its mean? So one would like to say that f minus the expected value of f is concentrated in an interval of small length. Well, let's see what we can do intuitively by appealing to that, omitting a few standard steps. But you see that 1 yi can change f by at most 1, right? Because each yi is of magnitude 1. And now you have to set up some standard machinery, which is the Dubs martingale from this. I won't go into this, but intuitively, each xi corresponds to the change in the number of bins by adding 1 yi. So note the yi's are independent, but the xi's are of course not independent. Okay? So if you pretend that what I said is correct, then I will get an interval concentration in an interval of length order root n. Right? This is not very good when mu is very small. For instance, when mu is little o of root n, the number of bins is a little over root n, right? And we are getting concentration in an interval of length longer than that. This is not very good. So we would like to improve this. That was actually not a very simple thing. It was a fairly long battle. And then Ray showed concentration in an interval of length root n times mu plus sigma. That proof was fairly complicated. And then Telegrand, in his classic paper, I will not state Telegrand's inequality, but I will refer many times to it and compare these results I have here with that, because it's a very nice paper and very classic one. Telegrand in his paper showed this with a much simpler argument. Okay? Then, as a sort of throwaway remark, asked whether we can prove concentration in an interval of this length. Now, why this? This is what you get for sums of independent, right? So if I just take the fraction sizes, which is an obvious lower bound on the number of bins you need, that's concentrated just by standard central limit theorem in an interval of this length. So the question was, is also the number of bins concentrated? The answer is no. There are very simple examples, and I won't show you an example, but that's simply not true, okay, that you can get this. What we observe here is, in appealing back to this, even though in the worst case, 1 yi can change the number of bins by 1, that's not the typical case. What is the typical case? So again, I would like to say a typical bound is all that matters. Again, I haven't stated the theorem, I'll state it in a minute. But what typically happens? Imagine packing these fractions one by one. They are about size mu mostly, which is very small compared to 1. So as you pack them, you'll have to pack about 1 over mu of them before you overflow into the next bit, right? So the probability that 1 yi changes f by 1 is only mu. So typically the change is 0 in the number of bins. Only with probability mu is there a change of 1, right? So I would have liked to put xi less than or equal to mu there instead of 1. Okay? That's my aim. But anyway, let me, before I state the theorem, the result we have is that, in fact, you get concentration in an interval of length, a peculiar looking interval of this length. And interestingly, I also have an example to show this is the best you can do. Well, this is for any finite number of fraction sizes. So the yi's are not allowed to be arbitrary. They are a fixed number of sizes, and they have to take on one of those values. But that is actually a fairly general case that has been well studied, and this is best possible. You can't do better. So you can't do as well as the sums of independence in this case, it turns out. Okay, probably at this point I should state the theorem. Should I? No, I won't state the theorem. I'll give you one more example and then come and state a proper result before I give you any more examples. The second example I want to talk about is the number of cliques of size L in GNP. GNP, some of you may know already, but it's a random graph with n vertices. Edge probabilities of P, they're independent, right? A standard model. And I would like to know how many cliques of size L there are. L is thought to be much smaller than n, right? So first, L equals 3. You want to count the number of triangles in a random graph with n vertices, edge probabilities P. Okay. So again, this has been studied quite a lot, and a lot is known. If you actually see this very nice book, there are lots of results here. One thing that is known, really, actually, for L fixed. So L is a fixed constant, n goes to infinity. This number, the distribution of this asymptotically becomes normal. That is a result of Rutchinsky. So the distribution, let me call this f of L. F is a random variable, but it's the number of L cliques in a graph, in the random graph GNP. The distribution asymptotically becomes normal. In particular, that means actually high concentration, because the normal is concentrated in an interval of length, the standard deviation, because normal is concentrated in an interval of length, the standard deviation. That's the best you can hope to get. you cannot get concentration in an interval of length smaller than the standard deviation because that's a standard deviation, right? So Rutchinsky's result, which is a classic, it's about 20 years old now, proves this.
What's the value of P here? Any particular value of P you're thinking of?
Actually, there's one condition on P, but P is large enough so that the number of cliques is at least 1. Okay. If P is really small and the number of cliques is going to 0, then nothing can be proved. Okay. That's actually all the conditions that Rutchinsky needs, essentially. Okay. Then I should say, in this, so this random variable is a polynomial in the basic independent random variables, which are the edge states, right? It's a polynomial of degree 3, and precisely for polynomials of independent random variables, these are independent. There are very nice results of Kim and Wu, okay, which also can prove this kind of concentration. I should mention that Telegrand's result cannot prove concentration, good enough concentration for number of triangles. It doesn't do that. Okay, that's because I should say for P small, the number of triangles is order n cubed P cubed. Okay, let's try to apply our Azuma, right? We take each edge as an independent random variable. Let's see how much an edge can change the number of triangles by. Well, in the worst case, it can change it by n, because by order n, right? Every such triangle may be missing before and now present when you throw in this edge. Therefore, you have a change of n per edge, okay? And there are n squared edges, so the root n is now another n. So this gives you a concentration in an interval of length order n squared, right? But you really would like, for small p, you would like a concentration in an interval of length n cubed P cubed or less, right? And that you cannot get. By the way, for P small, the standard deviation or the variance is n cubed P cubed. It's easy to see. So the ideal concentration you would like is an interval of length order n to the 3/2, P to the 3/2 for P small, because that's the standard deviation. Wu and Kim's polynomial inequality can prove such a concentration, but not Telegrand. And the inequality that I'm going to describe also proves a concentration of this interval, so the optimal concentration. But there's something more interesting. Rutchinsky's result is only for fixed L. Okay. Wu and Kim also only go up to L about, although they only do it for fixed L, but I think it can go up to L about log n over log log n. So if you're looking for the number of log n over log log n size cliques in a random graph, Wu and Kim's result can prove a concentration. Okay. But what I would like to say is, what I would like to show you is concentration when L goes up to log n, order log n. So in fact, the theorem I'm going to show you will imply a result that says even cliques of this size are concentrated. You could ask why log n, why is that interesting? And of course, the log n is interesting because if you have probabilities p which are constant, bounded away from 1, order log n is the largest size clique you can have. Okay. In G n half, the largest size clique is 2 log n, but in general, its order log n is the best you can have without the probabilities going all the way up to 1. So it's interesting to prove concentration results here. I'll state what I'm going to show you here precisely a little later, and I think it's time now to state the theorem if my order is correct. Yeah, in 15 minutes into the talk, we should be stating something. So, okay, good. Okay, so here is the result, and which maybe I should write it on this. So the result, now I'll state it precisely. So we assume that expected value of xi, we assume martingale differences again. Actually, I don't quite need this, but I will need something weaker, which I won't state, but let me state it under this condition. Let's assume that there are martingale differences. Now, I'm going to now keep my promise and deal with a typical bound rather than the worst case bound. So I want to say that the expected value of xi given x1 through xi minus 1 is Li. Well, I want to take moments of this, not just absolute bounds. Let me put absolute value. to the L, L sub L. Now, this is going to be the typical bound. What I mean by this is this holds with probability greater than or equal to 1 minus delta. The probability is on the fixed values of this, right? For every, so this is a function of x1 through xi minus 1. What this is saying is, except for a delta fraction or delta measure of x1 through xi minus 1, this holds. Okay. But you do have to deal with the exceptional events also. So expected value of xi to the L is always, in the worst case, ml. This is worst. So I do need both the typical and worst case bound. The point is the worst case bound is going to be much bigger, and I would, in the traditional Zuma, you would only have the worst case. Now I want to deal with also the typical case. Okay.
This is for a single value of L or all values of L, or?
This is for all L going up to a certain p, which is an even integer, and I'll have a bound on the pth moment of the sum. Okay. And the conclusion is, the conclusion is the expected value of 1 through nxi to the p is even, so I don't have to put absolute values here, let's assume. P is a high even integer. Okay. I like to say this is bounded. Okay. Now, here it's stated in terms of the exponential. See, this is proved by a traditional method called the Bernstein's exponential moment generating function method. I'm going to prove one of the sort of minor points. The major point is this typical versus worst case. A minor point is that it's nicer to use finite moments than the exponential moment. Why, I cannot tell you, because actually the proof, I have to go into the proof for that, which is pretty long. I don't think I'll do that. So conclusion is this, right? You have some constant depending on p, and then here are the important terms. So we get n to the p over 2. I'll write these down and then tell you. L2 plus m2 delta to the 2 over p plus n to the p over 4, L4 plus m4 delta to the 2 over p. So I should put p over 2 here, p over 4 here. Again, I will write this down and then explain it to you. Bear with me for a minute. Okay, so what is this saying? So the first is second moment term. The second moment term is n to the p over 2. So when I apply this, I will take the pth root on both sides. I will get xi. I will apply just Markov's inequality to this to prove that with high probability this is small. This is going to say, now I take the pth root, right? Let's take the first term. The first term now says root n times L2 plus m2 times delta to the 2 over 2. Okay. Omitting the other terms. Okay. Now what is this saying? Well, the first term, right, is what you would get from the central limit theorem, is what you would get there, which is root n times the variance. Root n times how much one thing changes. But usually you'll take the variance, right? However, now we took something smaller than the absolute bound or the absolute variance. We have taken the typical variance here. But there is a penalty for the worst case variance. We cannot escape that. There is a certain probability that will be worst case. But so this M2 is the worst case variance, which might be much higher than L2. But we are able to damp it down with the probability of failure delta. So point is, typically means with probability almost 1, this is the bound. Delta is very small. Okay? So I'm able to damp the worst case bound by delta. Not quite delta, but delta to the 2 over p. Okay? Now that's a result. Now there are higher moment terms. You cannot escape that. I'm bounding the pth moment. I must involve the pth up to the pth moment on that side, because as you go up, the moments can get arbitrarily higher. But the important moral here is the second moment is the most important because it's weighted up by n to the p halves, whereas the fourth moment is n to the p fourth and so on. So the power of n goes down. So you get what you might intuitively think of, which is the second moment is the most important point. So I hope the statement is clear. I won't prove this. The proof is a lot of sweat, actually. It's not that simple. At least I don't know simple proof. It's quite complicated. Although elementary, I don't think there's anything, particularly sophisticated going on, but it's quite long.
When you say with high probability, you mean polynomial?
Which high probability?
At the bottom.
Oh.
So is that not going to...
No, this is all precise, right?
No, I'm not saying that. I'm just saying, how fast...
Yeah. Oh, good point. So it's exponential. Okay, so maybe I should mention that. So in fact, the exponential moment inequalities are just convex combinations of finite moment inequalities, after all, because you can expand it into Taylor series. But more precisely, I should say the following.
Excuse me, do you mean the sum of the xi, the log down the...
Here? Oh, sum of the xi. Yes, you're right. Sorry. Yes, thank you. And then absolute value. Right, indeed. Yeah. So, in fact, you can derive... So, suppose you can ask, suppose there is actually an absolute bound. And let's say, let's throw in a variance also. Right? Then you can apply traditional summa. Now we have an absolute bound. You can apply traditional summa to get concentration in an interval of rank root n sigma. Okay. With exponentially falling probabilities. And in fact, you can get the same thing here. Okay. With exponentially falling probabilities. What you do for that is choose the optimal p. Sorry?
You choose p very big then?
Yeah, p will be very big. P will be linear in n. Actually, linear in n p. Sorry, linear in n.
Then you have to pay the m2 then, right?
Then you have to pay this, yes. I withdraw that p will be in linear n, but it's I don't remember exactly what p will be, but p is quite high. P is not constant. But that's okay when there's an absolute bound. Okay, so let me not go that route and instead state for you, we started at 410, right?
There's an absolute bound on this.
There's an absolute bound on the time?
Say 48.
What? I finish at 48.
Yeah, you can finish at 48.
By this clock.
By my clock.
Where's your clock?
You're wasting time. Right?
Oh, I'm sorry, yes. Yeah. Okay. Well, I should say here, there's a lot of work that I should refer to, but I don't mean to do a survey here. There's actually an interesting... So, of course, everybody has thought of using moments. It's not a new thing that one should use moments. There's a lot of stuff on moments, starting with Burkholder's inequality. I won't state all these inequalities, but there's actually a recent Annals of Probability paper by Lugosi, Massoretti. There are 4 authors, and I don't remember... On Friday, I would have remembered the name at my regular talk time, but now I don't remember the name. But it deals with moments. That's the latest on sort of Efrenstein, Burkholder type inequalities for this. The difference is that here we allow typical versus worst case bounds, moments, right? And that buys us something which is not quite present in that. The one place where it is present is Kim and Wu. They do have typical and worst case moments. They prove it only for polynomial functions, and it's actually a different kind of hypothesis they use, which I won't go into. I should go into something. Okay, so one other example where it's worth mentioning, and then I'll tell you the result on cliques. The example that all of these things cut their teeth on is longest increasing subsequence. So what you do here is, of course, you're given y1 through yn, which are independent random variables, uniform in 0, 1, for instance, and you want to find the longest increasing subsequence of this. That is to say, maximize L such that yi1 is less than yi2 is less than yil, and I1 is less than, and so on. Okay. It's known that let's call this f of y1 through yn. It's a random variable. It's known that the expected value of f 2 root 10 plus terms. A lot of work has gone into bounding, proving concentration results for this. Alan proved one of the first ones. What is now known is that this is concentrated in an interval of length n to the 1/6? N to the 1/6, right. Okay. And the proof is fairly long and specialized. I cannot prove this yet using my inequality. What I can prove is concentration in an interval of length n to the 1/4 with a simple proof using my inequality, and I'll tell you how in a minute. That's what Telegrand's inequality also gives you, n to the 1/4, not n to the 1/6. N to the 1/6 is more specialized work based on this particular problem. Now, how do you get the n to the 1/4? I can tell you that with these typical moments. First of all, if you apply traditional Zuma or martingale, what you get, well, the change in f because of each I is at most 1. Because if I throw a yi in, or if I change one yi, I can increase the length of the longest increasing subsequence by at most 1. Okay? Well, that doesn't give you much, but it gives you concentration in an interval of length order root n. Okay? That's why I guess Alan worked on it. You have to. What did you get?
I don't remember.
Oh, okay. No,
It was very good.
Whatever he did is forgotten anyway. So no, we get so. Sorry. So you have to work hard to prove concentration in a smaller interval than root n. Now notice that while this is true in the worst case, that's 1 yi can change the length of the longest increasing subsequence by 1 in the worst case. Okay, it's fairly easy to show that the probability. Now I'm going to be loose here. That 1 yi changes f by 1. Well, imagine I didn't have yi first and I'm throwing it in. A slightly different picture from the Doombs martingale, but let's not worry about it. I'm throwing one extra yi in. I could only increase the length of the longest increasing subset. I wouldn't decrease it. The probability that I increase it by 1 is not difficult to show, is less than or equal to 1 over root n minus I given this probability, given the previous one. So the suggestion is, so I fix the first I minus 1. I'm going to vary the tail, as always. I'm going to argue that the probability that the yi, which is also randomly picked, changes f by 1 for any fixed value of this is at most this. I won't give you the argument. I'll tell you this. Okay. Now, why does this help? Let's go back into there, right? xi is the change by throwing in 1 yi. What this gives you is the expected value of xi squared. So xi is 1 or 0, right? Either you change the longest increasing subsequence of 1 or 0. The probability that it's 1 is this much. The probability that it's 0 is the rest. So this is less than or equal to 1 over root n. Let's put. Let me put root n for now. It's actually the same thing. It will turn out when you saw. Okay. I claim that does the job. That's all you really need, right? Provided you believe me that the higher order terms are small, which in fact they are in this case. Only thing that really matters is this, right? Now, let's not worry about this. Let's worry only about the typical moment. Well, actually, in this case, it doesn't matter. But L2 is 1 over root n. Okay. And there are n of the, I have to take another square root to, there's a p over 2 there. So, or the other way of saying it is this is one variance of one thing, and there are n such things.
Bobby,
So,
x is y.
sorry?
X is y.
No.
No.
X is the Doombs martingale difference. So x is actually, you can think of it as the change in f when I throw in yi. More precisely, it's the Doombs martingale difference, but let me not define Doombs martingale. So it's the change, it's a delta I of f in a way. So it's 1 over root n, so you get n to the minus, what? But you have n of these, you have to add up, so that gives you a root n, and that's the second moment you take the root, you get the fourth, n to the 1/4. So you get concentration in an interval of length n to the 1/4. Now, this didn't actually quite use, this didn't use M2, this only used L2 there. Actually, M2 is all it used, L2 it didn't use. So in fact, there is room here for improvement. I don't know whether I can get n to the 1/6. I can get better concentration for certain other associated quantities. which is, there is a thing called the Hammersley particle move, which is really just dynamic programming that probabilists think of it as a particle system or something like that. But it's a dynamic programming algorithm to compute the longest increasing subsequence. And there are certain epochs in the dynamic programming. For that I can prove concentration, but not yet for LIS. Let's see, I have 4 more minutes. Now what should I do?
There's no penalty.
There's no penalty for ending early, right? Oh, I should state theorem 2. Okay, so this theorem 1 implies an inequality for what's that called? Bounded variation. McDermott calls it. So the setup is this: y1 through yn are independent random variables, and f is a function of these, right? And we would like to prove concentration for f, and we assume Lipschitz. Usually you assume Lipschitz. Now what is Lipschitz? Lipschitz says that f doesn't change much if I change one of the variables. But that's an absolute bound. You have to assume for any fixed value of the others, if I change the variable, the maximum change in f is at most a certain amount. Okay, so if you assume Lipschitz, and I call that delta, just change by changing one variable, is at most 1, then you get a concentration interval of length root n, right? That's a standard whatever inequality. But that's the standard inequality, right? Now, I'd like to state an inequality which, in the spirit of this, basically says that you don't have to assume an absolute bound. You just need a typical bound, well as an absolute bound. So maybe I'll state it more precisely. So y1 through yn are independent, and xi is not. They're not independent. Xi, this is Dubs martingale actually. So think of x. This is Dubs martingale. It's a standard construction. But if it's not at the top of your head, then think of xi as basically the Lipschitz. Think of it as a change in f, changing one coordinate. That's just as well as an approximation. It's not quite that. It is this, right? So we'll assume that there's an absolute bound on xi, just as normally we would, but we will also assume there is a moment bound. Expected value of xi to the q is less than or equal to q. Now there is no probabilities or anything. This is the absolute expectation. Well, xi is a function of y1 through yi, and I integrate out all of them. Okay, so that's just a number. Okay, and the conclusion is, with this, the conclusion is the expected value of f minus e of f to the p is again even, so I don't have to put absolute values there, is less than or equal to cp to the cp. C is about 20 so far that I have. It's not important what it is. So I get n to the p over 2 again. I'll write this down and then explain it. Q to the p plus 100 to the minus q r to the p. There's one more term before I write that. Let me explain what this stands for. Right? So what does this stand for? What would we typically get? So in for instance, inequality you have in McDermott's paper, this r, you would just have r to the p here. You would just get a bound of, I'll write this down here, n to the p over 2 r to the p. If r is 1, you'd get n to the p over 2. That would give you root n concentration, because you take p roots. 2 more minutes, right?
No, wait.
Oh, okay. So what this is saying is you don't have to suffer the r to the p. It's damped down with a probability here, roughly 100 to the minus q. If q is large, that's damped down. But you do have to suffer only q to the p, but q is a typical absolute value of q to the, I'm sorry, this is q to the little q. Qth moment is that. So typically xi doesn't exceed big Q. Sometimes it goes up to r. R is very large. You would have, the traditional result would have said this without the probability. Now you do have. One more term which is not very important, but let me It's got to be written down for. Sorry?
20.
Where is C?
CP to the CP, what's C?
Oh, C is 18.
Oh, it was 20.
20. It's about 18, and the big C on top is 6. Actually, it's more important what the C is. If you want actually,
I just,
no.
a constant.
Yeah, but just if you want Gaussian behavior in the limit, this P ought to be 1/2. I can only prove so far that C about 6. It would be nice to get it down to 1/2. Okay, there is this extra term which doesn't matter.
It's going down at such a rate, 2018, 6 in here.
Yeah. Now I won't state the results for cliques. Roughly, it says that the number of log n size cliques doesn't exceed, minus its expectation, doesn't exceed more than a factor times, more than 5 times its expectation. The probability goes exponentially small as the 5 gets bigger. Right? Okay. In the style of Eric, we let 5 be a variable.
Thanks very much.
Yeah, thank you.
Any questions?
Yeah.
Tightness.
Sorry?
Tightness of the bound, you mentioned it already?
Tightness for the log n size?
No, for the.
So for the bin packing, this is the best you can get. Because I have an example which shows that you can't do better.
Right example is bin pack.
Yeah, tight example is bin packing. Also, the number of triangles is tight. You get the best possible result. That's the standard deviation. The number of L cliques for L fixed, you get standard deviation, right? For small p. As a small p is an interesting case when p goes to 0. But for L log n, I don't get standard deviation. It's actually difficult to calculate the standard deviation.
I meant for the mixture, mu to the 3/2.
Mu, that's the best. The best bound in terms of mu and sigma is root n times mu to the 3/2 plus sigma for bin packing. Because there's an example which is not very difficult that shows that that's the best you can get.
So we're running short of time, so maybe talk to him afterwards, because it's almost 1 minute. Let's thank the speaker again, and then we'll get off.